This lecture we are going to discuss about what happens when we lower the antenna height. So what are the effects? Lowering the antenna height does not always reduce the co-channel interference. In some circumstances, such as on fairly flat ground or in a valley situation, lowering the antenna height will be very effective for reducing co-channel and adjacent channel interference. So however, there are three cases where lowering the antenna height may or may not effectively help to reduce the interference. On a high hill or high spot, in a valley, and in a forested area. So the three cases where lowering the antenna height may or may not effectively help to reduce the interference. You will see in which case the antenna, when we are lowering the antenna height, there will be reduction in the co-channel interference. We will see in the next slides. The effective antenna height rather than the actual height is always considered in the system design. So what is the effective antenna height is? I will show you in the diagram in the next slide. Therefore, the effective antenna height varies according to the location of mobile unit. So what is meant by effective antenna height is, I will explain you first. So here you can see in this figure, this is the height of the hill, and this means capital H. So and small h1 is the height of the antenna. You can see here the total height is called as, that is capital H plus h1 is called as the effective antenna height. So depending upon the position where the mobile unit is located, the effective antenna height will vary. So actual antenna height is nothing but small h1. I think you understood. So here once again I am repeating, effective antenna height is nothing but the place where the mobile is located, maybe hill or valley, that height we will consider, and also the height of the antenna we will take into consideration. That is called as effective antenna height. So in this case, in this figure, the effective antenna height is capital H plus small h1. So the reduction in gain resulting from the height reduction is G is equal to gain reduction is equal to 20 log. So effective antenna height by, this is the change in the reduction when we are reducing the antenna height, reduction in the antenna height and by normal effective antenna height. So here I have told you, when the antenna site is on a hill, that is here like this. We are discussing on a high hill or a high spot. So when the antenna is on a hill, as shown in this figure, the effective antenna height is small h1 plus capital H. So if we reduce the actual antenna height to 0.5 HL, that is here h1, the effective antenna height becomes not here h1, it is h1, yeah. The effective antenna height becomes reduction. The reduced antenna height, effective antenna height is 0.5 h1 plus capital H by effective antenna height without reduction. So after simplification, if the effective, that is height of the antenna is less than the height of the hill, then gain is equal to 20 log 1. So at that time it will become 0 dB. You can see 0 dB means this simply proves that lowering antenna height on the hill does not reduce the received power at either the cell site or the mobile unit. Okay, so the another case is, so now it is confirmed that on a hill when the mobile is there, even though there is a reduction in the actual antenna height, there will be no change in the gain. So in a similar way, we will see what happens the lowering the antenna height when it is in a valley. Second, this figure you can see, this is a valley. The height of the valley is h1 and the height of the where the mobile is he1. So we will see what is the formula to find out the gain in a valley. The effective antenna height as seen from the mobile unit shown in the figure just now is he1. You can see this is the effective antenna height as seen from the mobile unit. You can see it is from the mobile, which is less than the actual antenna height. So actually it is the actual antenna height. Here the effective antenna height less than from the mobile is less than the actual antenna height h1. So if we take he1, that is effective antenna height from the mobile unit as 2 by 3 h1, and the new antenna height is lowered to 1 by 2 h1, so then the new effective antenna height is, this is the half h1 minus of h1 minus 2 by 3 h1, that is 1 by 6 h1. So then the antenna gain is reduced by 20 log of 1 by this reduction in effective antenna height by 2 by 3 h1 new antenna height. So we will be getting minus 12 dB. So this simply proves that lowering antenna height in a valley is very effective. In reducing the radiated power in a distant high elevation area. So however, in the area adjacent to the cell site antenna, the effective antenna height is the same as the actual antenna height. The power reduction caused by decreasing antenna height by half is only -6 dB. You can see here 20 log of half H1 by H1. So from this we can say that there is a change in the when we are reducing the antenna height in the case of valley, but there is no change when the mobile unit is located on the hill. So next, coming to the forested area, the antenna should clear the tops of any trees in the vicinity, the area up to which we can see, especially when they are very close to the antenna. So in this case, decreasing the height of the antenna would not be the proper procedure for reducing co-channel interference, because excessive attenuation of the desired signal would occur in the vicinity of the antenna and in its cell body.